Hello, welcome to our CST 105 Milestone 3 discussion. So I have in front of us the Milestone 3 requirements, and there's pretty much two requirements: create a UML diagram and then write the code for the object classes needed for the game. So I think there's two requirements in one there. One, the UML diagram, which you'll find is based heavily on the work that you did for Milestone 2. UML is Universal Modeling Language. We'll discuss that in a separate lecture. It's more formal than the abstract data type you worked at on Activity 2. It also concerns itself with some implementation details, which the abstract data type explicitly avoids discussing. We will review how to do the UML side of that, and then write code for the object classes in your Unigame. So you'll need a minimum of 3 classes. This is why we looked at Milestone 3 when we did Milestone 2, because this defined the classes that we documented in Milestone 2. A card class, a hand class, and a deck class. We'll see that there's at least one more class that's required. You made other classes as you see fit. So this is the first time you're going to actually produce Java code here when you create these classes. So the next instruction: test your program by running a console application, a driver program, that creates a deck of Uno cards, deals the cards to 2 or more players. I'd like to see 4 players, and displays the contents of each player's hands. Create a video in which you demonstrate your project and explain the interactions among the objects. So these requirements ask for you to do the UML diagram and then write code that essentially sets up the game. No play yet is required here, but the play is ready to begin. The deck is created, the discard pile is created, and the player's hands are created and they're populated with cards. The game is ready to start playing. Now, if you can get some gameplay going in this Milestone 3, that would be highly desirable for you. Because when you start considering the special cards for Uno that you also need to support, that takes a long time. Let's take a look at the Uno cards for a moment. So I created this document, and I'll post this as well to make it available for you. I looked at the rules of the internet.com Uno rules, and they have descriptions of these card types, and I wanted to test the exact numbers of the cards. So there's red, blue, yellow, and green colors. There's 4 colors. So 0, there's 4 zeros of one of each color. So that's when you see 4 in this document. That's referring to color. So 1 through 9, there's 9 cards, 4 colors, and there's 2 of each card. And then the active cards, or the action cards: skip cards, 4 colors, 2 of each. Take 2, 4 colors, 2 of each. Reverse, 4 colors, 2 of each. So those make 8 cards in those categories. And then there's black active cards, that is, cards that don't have one of the colors red, blue, yellow, or green. In fact, these are wild cards who the color is called as the card is played. So the wild card, 4 of those, and the wild card plus 4 of those. So I'll make this available to you too. But as you think about getting this to do gameplay, think about first supporting the normal cards 1 through 9 and 0, of course, things that don't have actions to them. If you can get your gameplay up to that standard, where let's say the active cards are essentially played like they were some type of number that matched the color, and the wild cards match anything but don't necessarily call out the color, but they could. In fact, I think it would have to. So thinking about how the wild cards behave, their color is called as they are played, and you can think of an intelligent way to think of that, or just an arbitrary way to come up with the color of a wild card. It has to be assigned to color for gameplay to continue. So you could just assign yellow at all times, or an arbitrary color for the first round of this. So get normal gameplay going, and then for Milestone 4, you could concentrate on the active cards. Again, you are just required to set up the game and not do any gameplay. It's to your benefit to support gameplay. Next, we're going to look at some code I developed that plays a card game with a standard playing cards. So here's my card game, Milestone 3 demo, a war game. So if you've never played the game of war, 2 players get half the cards each, 26 cards apiece. And then you, very simple game, you place down cards and the higher card wins, takes both cards. If the cards are equal in value, then you deal down 3 cards, the players each deal down 3 cards apiece, face down, and then 1 card is revealed. And the winner of that match wins the entire stack of 10 cards, the original 2 cards plus the 3 cards dealt, plus the 2 cards that were the deciding cards. If there's a tie, then that process continues, and it's winner take all on the last card that's revealed. And then the play goes back and forth until one player has all the cards, and that's the winner. So that's what this is going to demonstrate, some actual gameplay. So let's start with the innermost, what I think of as the innermost class, this card suite here, our card suit here. So normal standard deck of playing cards, not the Uno cards. So when you see this, you're going to have to modify it for the Uno game, of course. So have club, diamond, heart, and spade here. Using the enum, I think, makes a lot of sense. You can use integers, but in order to get that self-documenting behavior and a lot of things done nicely for you, I would encourage you to use enumerations. Card value, 2 through ace. For the card value, it's another enumeration. And now let's take a look at the card class itself. So the card class itself is our first class that we're going to discuss. We see its constructor that takes the suit and the value here, and it sets up the internal suit and value for the particular object. And then we have getters but not setters. That can be different for your behavior. So I have read-only behavior here. So the game itself is not able to set the card, change the card values, the suit or the value, once the card is established. We have a two-string method, which is a special method. We'll discuss more of that detail later. But it's a special method, and it's used to convert a particular object into a string so it can be printed in a UI. And here I have this two-string method to print out this card with its suit and its value. And then we have these private implementation details with the suit and the value. The next logical class is the deck itself, which is, of course, is made up of cards. So here we have a deck, and its constructor creates a new array list of card, so the class we previously looked at, and it's empty. So the constructor creates that data structure, the array list, here, object, but it doesn't populate it. The method on line 10 populates the deck, and you can see that from the enumeration, we get values, and we have an array of all possible card suits, an array of all possible values. And then we loop through those arrays in an internal loop, going through the values on the internal loop, given a fixed suit. So looping through all suits, and then looping through all values on the inside. Then the card is added to the deck, the object that was created here, one at a time, via this constructor. So the populating of the deck will create the deck all in order, just like a brand new deck of cards would be from the manufacturer, from the printer. So we have a shuffle method. And here, the Java collections class has a very nice method for it. It's called shuffle. So all we have to do is call the collection class shuffle to get a randomized deck of cards. Here we have the deal card method, and that removes a card at the top of the deck and returns it. So the remove method that's inherent in the array list does that for you. It removes the object and returns the value of the object removed. So very convenient for deal card there. Has card, as long as card's.size is greater than 0. This is a boolean that returns true or false. So we have a two-string method for the card, or for the deck, that relies on the two-string method for the card. So when the code sees this cards array list of cards object, it knows the two-string method of array list, and then that drills down into the two-string method of the objects that the array list contains, in this case, card. Okay, the next logical thing to discuss is the hand itself, which is over here. So the hand has a lot of similarities, as you can imagine, with the deck. Its primary internal data is an array list of cards, just like the deck. And here, the hand constructor does something very similar. It creates the empty array list. Then we have draw card. So as, let's say, cards are dealt, the card is taken up and added to the collection. Has card is there's a size greater than 0 in the hand. And card count. We'll see how this is used. Essentially, the cards.size reveals the card.size method. And then add cards. This adds an entire array list of cards to the collection, add all. So that's different from the add method or draw card method that just adds one card at a time. And then when we play a card, we remove the first card in the hand and return it. And that's returned here, also using the same remove method, except the index is fixed at 0. And then here's our two-string method. Remember, the two-string method will convert it to a string when it's printed. And again, the hand two-string method goes to the array list for cards, and then that has a two-string method that drills down into the cards two-string method. So if you need to modify your two-string methods to get a different result, it's primarily the action is in card. So now we have card, we have deck, and we have hand. We're ready to look at the game method, or the game class. So the game class has exactly one method. And I need to use a lowercase b here to adhere to Java standards, so I'll change that at some point. Here we have the play. We create the deck, now populate, print the deck out. That uses our two-string method that we discussed, and we'll see how that works. We shuffle the deck, and then we print the deck. Then we create our array list of hands. There's only 2 players ever in war, and then they get all the cards. Right. So here we go. Let's back up a little bit. I want to look at deck.populate here. So deck.populate takes the card suit of values, that is, it's an array of all possible card suits in an enumeration. Remember, this is an array of card suit type, and this is an array of card value type. So, and this is a factory method essentially that produces that array, and so then we loop through them. One warning about this. A standard card deck is very regular. It has equal numbers of all card values and equal numbers of all card suits. So that's why I can use a tight and simple little loop here to correctly populate a standard deck of playing cards. Remember that the Uno Get deck does not have equal numbers of cards, so you can't just straightforwardly use a for loop like this. You need to make either cut into the for loop with logic that prevents some cards being added. Alternatively, you could just write 108 lines of code that explicitly have a constant in suit and value and create one by one each individual Uno card 108 with 108 lines of code. That might actually be preferable to trying to construct loops with logic, with conditional logic that says don't add this, don't add 0 card, but because we've already added enough 0 cards, for example, and other cards that have less than the cards that go from 1 to 9. Just an idea. You can, of course, implement it the way you wish. Just make sure that you have 108 cards when you're done with populating, just like I make sure that this has 52 cards done when I'm done populating the deck. Let's get back to gameplay now. So we deal out the cards. We print them out here. So each hand is printed out. This will loop through the array list of hands and print them out for us. I have winner here is -1. Here I'm not using a Boolean value because winner is actually going to be the index value of the winner when that's determined 0 or 1, player 0 or player 1 internally, and I'll portray that to the user as player 1 or 2. Then turn winner means that winner was decided by in the war game when players have to deal out 3 cards. Running this several times, turn winner is almost always true at the end of this. That's when the winner is decided in the game of war. And then I have a turn count, so I can print that out. Winner is as long as winner is equal to -1 and turns is less than 1,000,000. It turns out that war can end up in an infinite loop, where what I've observed, each player ends up with 26 cards, and they're equally matched, and they'll turn them over forever. So I stopped the game at 1,000,000. I never, of course, ran it forever, but it looked like the game had stabilized. So the winner can be determined on the turn, and we'll see how that happens. And then we count the turns. As long as winner is -1, that is, the turn didn't determine a winner. Then we loop through each of the hands, getting a card as long as there's a card there. So it tests for winner. If let's say the last turn emptied them out of cards but didn't determine a winner, this would determine a winner here. As soon as the card value reaches or has card is false, then a winner can be determined. And then every 10 turns, I print out the who is winning at the time. And then if winner comes out to be not equal to -1, I have a turn winner of true. And then that ends the loop here. Winner becomes either 0 or 1. That ends the loop. Or turns is equal to 1,000,000. That will stop the loop also. So if winner is not equal to -1, I have a winner. And I print out the winner, and we have no winner. And then I print out the hands so I can analyze what was in each player's hands on that. So let's run this a few times. So we saw this game took 571 turns to determine the winner. Player 1 has you can see that player 1 has established himself or herself as the winner. Here is the initial deck of cards, and you can see this is the non-shuffled deck of cards, and then the shuffled deck of cards that I printed out earlier in the code that we saw that, and the two hands of each with 26 cards, and that's the result of the two-string method. And then at 10 turns, every 10 turns I replace, and you can see as the battle played out. As I looked through some of the games, there were definitely times when it looked like one player had all the advantage and it turned around during the game. And this time it took 571 turns of this extremely boring and pointless game. Let's run it a couple more times. And see 301, and this is when it's either I've seen some games be less than 100, some games be more than 100, and occasionally it'll go into what seems like a non-terminating game, and it seems we've just landed on one. Notice that each player, it looks like it has 26 cards, and then once it did 1,000,000 turns, right? So I'm printing out every 10th player with that modulo value. Whenever the counter is evenly divisible by 10, I print this out. So that's why this is evenly divisible by 10. And you can see the players have come up with 26 cards. Let's get to the end of this thing. And then you can analyze this if you were interested in it. You know, as you start running computer programs, you can turn up all sorts of interesting analytical possibilities, including why did this? I did read that a mathematician had theoretically determined that a game of war could end in an infinite game. Maybe I have a bug, but I think this shows that at least that theoretical prediction was true. Taking 1,000,000 hands, and I've never seen it when you got to 1,000,000 hands, both players end up with 26 cards. It's exactly equal. So there's a lot of interesting behavior buried in this very simple and boring to play game. So good luck on Milestone 3.